I've
Yes.
started recording, but I may break any time.
Okay, no problem, Dr. Kiran. Jayes will take care. So, Jayes, go ahead.
Yes. Yes.
Sure. So a very good evening to one and all, and a very good afternoon to Dr. Farhad. We are assembled here to have this scintillating talk, which will focus on the security aspects of embedded systems. Now, we will essentially look at the protection of the design from third-party design houses and foundries. We'll also discuss the logic locking tools developed at the Institute for Communication Technologies and Embedded Systems. In the second part of the talk, we'll focus on the development methodologies of low power, high performance embedded systems. These methods, for use for non-Van Neumann computing models, where the computations are performed inside the memory to reduce data movements. So this is a basic abstract of what the talk will be about. And to introduce our speaker for the day, Dr. Farhad Merchant is a PhD from Indian Institute of Science, Bangalore, in 2016. His PhD thesis title was Algorithm Architecture Co-Design for Dense Linear Algebra Computations. He received the DAAD fellowship during his PhD. He worked as postdoctoral research at the Nanyang Technological University in Singapore from 2016 of March to December of 2016. In the December of 2016, he moved to corporate research in Robert Bosch in Bangalore as a researcher, where he worked on numerical methods for ordinary differential equations. He joined Institute of Communication Technologies and Embedded System, RWTH, Aachen University.
I think there is some problem with the connection, so maybe I can just start because it's already 5
Sorry,
minutes.
One last sentence. Farhad is also a recipient of the HIPEC Technology Transfer Award in 2019. We welcome you and we are honored to have you here, Farhad. Over to you.
Okay, thank you. Thanks a lot, Jayesh, for the very nice introduction, and thanks for invitation, Ayan. I'm not sure if you're there. I think you're there today, right? So, okay.
Dr. Farhad, just a small request. If you could also switch on your camera, it will help.
Oh,
If
sure.
it is okay.
That's fine. Yeah. No. Okay. Then I'll have to turn on the light. Yeah. Okay. So I hope I'm visible. Hello, everyone. As introduced, my name is Farhad Merchant, and currently I'm a postdoctoral research fellow at the Institute for Communication Technologies and Embedded Systems. And in my talk today, I'll discuss about the security aspects of embedded systems, and then I'll also touch upon neuromorphic computing. So I'll stay a bit brief in the field of neuromorphic computing, as we have recently started working in this domain. But in case of in security, we have been working now since last 5 years, so I have a lot to discuss. So before we go into the details, so maybe I'll first introduce my institute, the work we do. So we are not restricted to security or neuromorphic computing, but there are a variety of fields that we pursue as a research, and so I'll discuss all the work that is being carried out at our institute, and then I'll go to hardware security, and then I'll discuss about our laboratory that we are now trying to develop called NeuroLab. Right, in the bottom picture, what you see is our institute. So this is a 6-story building, and we mostly occupy 4th and 5th floor in the building. And yeah, so here you see the entrance, and so This is our geographic location. So this is where the Aachen is now. And here, if you see, it's actually at the meeting point of 3 countries, so Netherlands, Belgium, and Germany. Also, Luxembourg and France are not far enough. So yeah, the look in terms of location, we are pretty well, basically, I would say, because we are pretty close to Belgium. We are very close to Amsterdam, Frankfurt, so Stuttgart, so kind of very close to all major European cities, at least in the Western Europe, right? Um, okay, now let me discuss briefly about our institute. So our institute is co-headed by 2 professors, Professor Rainer Leupers, whom you see here in the first row, second from the left, and Professor Harris Gatchanin, who is first in the first row. And we also have 2 emeritus professor, Professor Gad Ashaid, who retired last year, and Professor Meyer, who retired probably 10 years ago. And so Professor Ashaid and Professor Meyer, they mostly focused on signal processing and also on the architectures for signal processing. While at our institute, which is called SSS, which is Software for Systems on Silicon, here you see in the second row, I mean, in the third line in the slide. So we focus mostly on computer architecture and tools. And Professor Harris Gachanan, who is heading distributed signal processing institute, is mostly focusing on signal processing aspects, so focusing mostly on the algorithm side. We also have 2 guest professors, and then we have around 20 PhD postdocs. And yeah, I'm one of them, so you already see me in the as one of the postdocs here, right? And then we also have non-academic staff to help us in a lot of administrative procedures. So this is our mission. So I see mission, or I would say philosophy. So we look into applications and we look into design automation tools, and we also look into hardware and software implementations. And in the middle, what you see is different application domains. So basically, it's a trinity. So we focus on 3 different things. So we look into applications, we look into hardware software co-design, and then we also try to develop tools for it's a high level synthesis or parallel programming or logic clocking recently. So these are the 4 main topics at SSS. So in our institute, one is programming tools. So where we mostly focus on developing programming tools. We also had in the past, we also had some major projects for parallelization of legacy codes, sequential legacy code. A second one, what you see is the system on chip system on chip designs, where we mostly focus on ASIC and ASIC prototypes. We also do a lot of work on virtual prototyping. So virtual prototyping, many of you might have already heard about it. So virtual prototyping is basically used to do early software development on for hardware. So before you fabricate your hardware, or before you give it to foundry for fabrication, it is highly recommended that you also start doing software in parallel. And the 4th topic is hardware security, which is something that we started 5 years ago. So yeah, so when I joined, it was pretty much a new topic, and I started looking into different aspects of cyber hardware security. And in this presentation, I'll talk one of them, so which is logic locking. But I also work on other topics such as runtime malware detection and yeah, other aspects such as physical unclonable functions, etc. So yeah, so this is our funded project portfolio. So we have quite a few completed projects, because our institute is fairly old, I would say. Um, and we mostly try to balance our funding between funding from German government, funding from European Union, and funding from industry. So what you see in this pie chart on the right is that we really try to balance the funding from different funding agencies. We have quite a few active projects. So Neurotech, Anaconda, BioNanolog is one of my projects where I'm the PI. We got it last year approved. We also have EU projects, Tetramex, Hypeak. I don't know if some of you might have heard about Hypeak, which is basically a Europe-wide network, and it provides a lot of it provides platform to a lot of people to build collaborations. Tetramex is also quite an interesting project, because it provides funding to SMEs and academic institutions to transfer their technology to large scale industries. And yeah, so this is how our technology transfer pipeline usually looks like. So we usually start from very basic research or fundamental research that matures into some successful R&D. Um, so that is basically building a first or laboratory prototype, and then from there we do some applied research and development, and then eventually we prefer that our technology is transferred to the industry. Right. And at different stages of the pipeline, we have funding from different agencies. So for example, TFG funds fundamental research. Then there is a funding agency called BMBF, which is also a German government agency. This is just an example again, which funds more of applied research. And then we always have EU funding, for example, Tetramex, to transfer our technology to the industry. And here what you see is the different companies. So this is again a small set of companies where we usually transfer, where we have transferred our technology in the past. And in return, of course, what we expect is that we get funding from the industry to run our projects and to continue our successful research and development. Right. Spin-off history. So basically, RWTH Aachen University provides a very good platform to have a startup, and that you can already see. So this is like, I can already count. There are 7 startups. There have been 7 startups till now, and I would say I'm pretty much aware of the ones from Lisa Tech onwards. So the Cadis, Atcom, and Access, they're already most of them are now already acquired long ago. So Cadis was acquired by Synopsys in 1994. I think even Synopsys was new at that time. So coming to Lisa Tech, many of you might have heard about the Synopsys Asset Designer tool, and it has its roots in Lisa Tech. So 50% of the tool actually comes from our institute. And it was acquired by Cover, a company called Cover in 2010, and then later Cover was acquired by Synopsys. Yeah, one more startup is ICE Gateways, which is basically startup of Professor God Ashide, who is now retired, and the focus of the startup is more in the smart lights for the smart street lights, basically. Yet another startup, which was in 2014, is Silexica. I'm not sure if many of you might have already heard the news that Silexica got acquired by Xilinx, I think last month only, which is again one of the very good success story. So the focus of Silexica was, so when they started, the focus was more into building parallel tools for parallel computers, and then they also looked into high-level synthesis for FPGAs. One of the recent startup is called Secure Elements, which is based in Munich, and Secure Elements and a company called Hensoldt, which is a German company. They have a joint venture called Hensoldt Cyber, and that's where we recently did some technology transfer for our logic locking. Yeah, so these are some of the sample products. So the one on the left I already talked about. So that's the one which is Synopsys Asset Designer, and yeah, so that's one of the product which is very well received by many customers of Synopsys. And on the right, what you see is one of the recent one, which is called MIG-5, which is so MIG stands for Made in Germany, and it is based on RISC-V core. So I'll anyways discuss the technology that goes into MIG-5. Okay, so then let's switch to hardware security. Yeah. So, hardware security, many of you might have gone through some recent news items where, so recently I think a couple of years ago, there was some news that there was some Trojan mounted on some Amazon or some Apple chip or PCB. So although eventually it was denied that there was no such thing happened, but yeah, it came in the news, and obviously if it is, I mean, obviously no company would really accept or that they planted the Trojan, or no company would really accept that there was Trojan detected in the chip, right? Because it's a big business loss for them. So now So hardware Trojans are basically malicious circuits which are inserted in your design while the design is in with a design house or fabrication facility, and this kind of Trojans can perform many malicious activities such as information leakage, reliability degradation. So there are Trojans that can really age your hardware much faster. Or as in our case, it could also be some kind of denial of service attack. So then there could be a Trojan that could just invoke a kill switch, and your hardware just stops working. Right. So recently, it has also been noticed, at least in the scientific community, that the number of Trojans are really increasing. And one thing is one thing that we definitely claim here is that detecting a Trojan is probably not possible, because I mean, if you look at the Trojan, it could be anything, right? It could be a small counter that can just trigger one instruction, or it could be some antenna that does some information leakage. So now if you look at the variety, the detecting such Trojans is nearly impossible. So then what do? We focus more on prevention of insertion of hardware Trojans, and that's where we claim that okay, there are class of Trojans that you can at least prevent. Right? So you can't really prevent unintelligent Trojans that are inserted in your design, but you can definitely prevent Trojans which require the attacker to understand your design. Yes. So now coming to the IC supply chain or integrated circuit supply chain, this is how it looks like. So you basically start with your specifications. From your specification, you go to hardware design. So you do RTL design. Then you do logic synthesis. From logic synthesis, you come down to physical design, and then you do fabrication. Right? And then from fabrication, after fabrication, you do assembly, you design your PCB, and then eventually what you do is you do distribution and integration, and then you're ready to sell your product basically. Right? Um, Now here, what you also see some segregation between IP owners, foundry, and assembly facilities. So here you see that while you're in during the supply chain or in this cycle, your design goes through multiple entities, right? Some of these entities can be trusted, while some of them you might not be trustworthy, right? And that's what DARPA defines as a window of vulnerability, right? So usually the design house that does the place en route, or the fabrication facility that is fabricating your design, is usually considered as in the window of vulnerability. Okay, I think we have a question here. Where does the embedded engineer fit in this chain? So the embedded engineer can fit at multiple places. So you can also be IP owner. So let's say if you have for example, if you're working in a large organization, so you could be somebody designing specification, or you could be somebody doing RTL coding, or you could be somebody developing firmware. So there is I mean, you can fit anywhere. Embedded engineer could also be at the end a field application engineer who is going to customers and solving their issues. So yeah, embedded engineers can be anywhere here. Yeah. So yeah, so this is basically one window of vulnerability defined by DARPA, and our focus is mainly to save the design while it is in this window of vulnerability. Right. So now, how do you prevent somebody from understanding your design? So for that, we need to understand what kind of vulnerability we are trying to protect against. So what we are trying to protect against is a hardware Trojan, as I described before. Now, but what kind of hardware Trojan are we trying to protect against here? So can we protect against somebody inserting an antenna? Probably not, right? Because this is something which is undetectable, or it could be detected by some other means. So for example, something like ATPG test. right? So what we are trying to protect against is meaningful or controllable and design specific hardware trojans. So now uh, now this kind of trojans are really deep and stealthy inside the circuit, right? And this kind of trojans cannot be detected by the normal or the standard procedures or standard design and test. So our objective here is to prevent the attacker from performing reverse engineering of our design. And so how do we do that? So for that, what we do is we increase the complexity of the design in such a way that the reverse engineering is almost not feasible or impossible, right? So now to increase the complexity of the design, what we do is we adopt a methodology called logic locking. So this is a very small example of logic locking. So it's basically a toy circuit, right? So on the left side, what you see is the original circuit, and on the right side, what you see is the locked netlist or locked circuit. So what we have done basically here is we have inserted these gates, this XOR gate and NOT gate, and the input of this XOR and NOT gate combinedly K1. So this is basically a XNOR gate, and the input of the logic gate of this key of the gate XOR gate and NOT gate becomes a key input. And unless you supply the correct input here, your circuit will not give correct output. So now the correct input here would mean that the the extra added design is basically acts as a buffer, right? So this is how logic locking works, right? So now this is a small design, but when you talk about, let's say, processor, right? So the design could be really large. It could be millions of gates. So then you definitely need tools to insert to read your design, you read your netlist and selectively insert logic gates there. Right. Now, before going forward, let's discuss briefly about the attack model. So what kind of attack model are we assuming here? So now, um, let's say I'm the IP owner and I want to get my chip fabricated, and probably I don't have enough money to do design to do place and route. So then I have to also hire a third party or a company to perform a place and route, right? So now when I give my design to the company that does place and route, what kind of design should I give that company such that they're not able to understand? So that means I'm now trying to define the powers of the design house and the foundry. So what does the design house have? So it has access to the locked netlist, right? Because since I want to protect my design against insertion of hardware Trojan, what I would do here is I will lock my design and give it to them. So now the design house and foundry, they do have access to the locked netlist. Also, they know where the key inputs are, right? And probably they also have acted or they also have access to the activated chip. So for example, let's say if you realize that Intel's Core i5 processor is logic locked, and then you'll easily get it from the market. So now the fabricated chip that you get from the market is basically an Oracle, right, which is already activated chip. Okay, now that brings us to a new debate. So there are two types of attack models. One is Oracle guided and another one is Oracle less. Now in case of Oracle guided attack, the Oracle is available in the market. So that that means that you know the inputs and outputs. So you know the functionality of the design, right? And now you also know the key inputs. Now what you can do with the design. So let's say you have a net list and you have a fabricated design. And now you know so now since you have already fabricated design at your desk, you know what is the functionality of the design. So now what is missing part? It's the key inputs in the netlist, right? So you can easily apply Boolean satisfiability test or set attack and retrieve the key, right? And it has been shown in the literature that it is very easy to apply this this kind of attacks and retrieve the key, right? And yeah, now, but it was shown recently that now to retrieve the key, you really don't need to do set attack at all, right? So what you can do is, if you have access to the physical, if you have access to the fabricated chip, you can probably you can probe it and you can read the key out. There is no need to do fancy set attack, right? You can do some apply some optical attack, and you can read out the key, right? And that's what has rendered this Oracle guided attack, which I would say kind of not so useful, right? So then we decided to start looking into more powerful model, which is called Oracle less attack, right? So now, in case of Oracle less attack, what happens is that you assume that there is no chip available in the market, right? Also, one thing you'll notice in the Oracle guided attack, you're assuming that it's a high volume production, but it's not always necessary that it's a high volume production. It could be low volume production as well. So now, in case of Oracle less attack, what we assume, or what our attack model says, is that the foundry or the design house does not have access to the uh, to the fabricated chip, or so there is no availability of Oracle, right? And now what foundry or design house are, what they're trying to do is they're trying to retrieve the key from your locked netlist, which is quite interesting. So it might some someone might feel that it's not possible, but I'll show you in the next slide that it is possible. So yeah, so as I said, the activated IC is not available. So now when we talk about Oracle less attack, we basically try to exploit structural features of your netlist or of your design to understand the design and to identify the key gates and the key, right? So maybe before going next, I'll just check if there are any questions, and I
There
see there
is
are some
one question
questions.
actually, Farhad.
Yes. So in this design, okay, first of all, you don't need to call me sir. I'm quite happy with my first name. So maybe you can call me Farhad, and that's what I also prefer. So in this design of logic locking, the output function will not change. So okay, so I did not really understand the question. So maybe you can unmute the person who has asked the question, and you can ask question probably in bit more detail.
Sure, I'll. Hi, so the person who asked the question, you can please please.
Hello, sir.
Call me
Your
Farhad.
voice is breaking,
Okay.
sir. Farhad Merchant, sir.
Yes, my voice
Your
is
voice is
breaking.
breaking.
Okay, that's bit. Okay, so now tell me, is it still breaking?
No,
It's
it's good now.
feeble. It's low.
It's good.
Okay, so I have two different answers here. So
We let HP complete his question.
yeah, sure.
Then we'll see.
Yes. Okay, so I don't hear any question.
Uh, uh, I was talking about that in the concept of logic blocking. Means we are giving a key input. So for that reason, the output will not change for that K1 input.
Yeah, so if you supply wrong K1, so if your key is not correct, your output will be corrupt, right? So if your key is correct, that means that the extra added circuit would act as a buffer, right? So you'll get correct output, right? So now if this XOR gate and NOT gate act as a buffer, then output of G1 would directly go to G5, which is the original circuit, if you see in the left, right? But now if you give a wrong key input, then your output of your KG1, right, will be basically the the inverted output. Okay. Okay, so if it is clear, then let's go forward. So we discussed this Oracle less attack.
Yes, sir. You
Yes,
can
so
continue.
yeah, sure. So
Your voice is
okay,
clear.
yeah. So yeah, so this is about reverse engineering. So we just discussed about Oracle guided and Oracle less attack. So now, so in our methodology or in our tools, we mostly go for Oracle less attack because it is more powerful. Um, yeah, so yeah, now coming to the reverse engineering problem. So this is how you would. So now you have your netlist, and then you partition it um, into multiple modules, right? And I'll come to it. Why would you do this? So then you do some kind of clustering, and then you decide what are your modules, and then you also decide your module boundary. Now from that, what you do is you get a lot of modules in the design, right? And then now these modules are basically interconnected. What you see in the middle is just for the representation purpose, right? And and then yeah, so now in our approach, what we do basically is that we we take these modules, and then we supply. So now in our design, the design has a few external key inputs, and then we have a uh, uh, for from each module we generate a part of a key for the other modules, right? So let's say if I have here 5 modules, module 1 to module 5. So module 1 will generate key for module 2, module 3, module 4, and module 5, right? So similarly, module 2 will generate key for module 1, module 2, module 4. uh, Sorry, module 2 will generate for 1, 3, 4, and 5, right? And similarly, each module, so we'll try our best to have as much as key generated from this intermodule communication as possible. And apart from that, we also have key that is coming from outside. So now here, if you see, one thing is the key is pretty large. Now the second thing is, now since a lot of majority of my part of my key is coming from other modules, right? So unless my whole design is activated, right, I don't have correct key. So that means breaking design into my so that means I cannot really do attacks on modules, right? So that's the major that's one major takeaway from here. Right, now the second major takeaway here is that you have to consider design as a whole, right? So that means performing an attack is nearly impossible. Right, and this is our approach that we call interlock. And this was published in 2 conference papers. So one was in European Test Symposium, and another one is architecture uh, for some computing systems. Yeah, that was conference in Aachen only. And uh, yeah, so in the first paper we focused on 32-bit RISC-V core. So we took the RISC-V core from ETH Zurich, from the Pulpino platform. So they have RISC-V core now. I think it's renamed, and we locked it. Now in our second paper, we took 64-bit. Back then it was called Ariane core. I think now it is CVA64 core that we logic locked. And then this is also prototyped on FPGA. Not just that, it's also the chip is also fabricated by our industry partners. So now this is something which is commercially available. So on the left side, what you see is the chip diagram, and on the right side, what you see is the development board. And this is available from our industry partner called Hensel Cyber that I mentioned in our spin-off history. Now the features of this board are that it has a 64-bit RISC-V core. It is also running an operating system called CentOS. So the CentOS is an operating system that is developed on top of a microkernel called SCL4. SCL4 is a kernel which has different philosophy compared to Linux. Right. So now in ACL4 you get very good isolation among different processes, and if your one process is manipulated, then there is no impact on other processes. So that's the advantage. So it has this horizontal model instead of this one monolithic kernel that Linux usually has. And now this design is fully logic locked, right? So I cannot give you details about the key, but the key is fairly large, and I can guarantee you'll not be able to break it. Right. So this is the design that we claim to be Trojan free. Right. Now comes the next aspect of our work, which is fairly recent. So recent as in this is most of the work is done in last 1 year. And since there is rise of machine learning, so we all have to talk about machine learning, right? So then what we thought is that we are assuming this Oracle-less model. Now, can we apply machine learning attack, or can we try to retrieve key from netlist by applying some kind of structural analysis attack, right? So that's what we try to do here. Yes. So now what we did is we develop a tool called, or we develop an attack called snapshot. So now in snapshot, what we do is we read we read so from the key input, you basically you track your key gate, and then you create a locality graph, and based on that you try to predict your key bit, right? And yeah, so and we also borrowed some ideas, considering that CNNs are quite efficient. We also borrowed some ideas from image processing. Right. So here the idea is to learn on label localities and then try to predict the key bits for different key inputs, right? And yeah, so this is we also involved some genetic algorithm principles here to arrive at the best machine learning model or machine learning parameters that we require to predict the key bits, right? So and yeah, so this is a full complete tool which is available with us. So usually we do not make it open source because of our we have very close ties with industry. But yeah, but this is in a way this is, I would say, publicly available because it's already published. So the paper was accepted in SEM JETC, which stands for Journal for Emerging Topics in Computing. So and with this kind of attack, we tried a few benchmarks, and we had quite astonishing accuracy. So now we tried some standard benchmarks such as ISCAS 85 and ITC 99, which are used for design and which are used for test basically. And we performed XOR or XNOR based logic locking to read or to predict the key, and we could go up to 80 or 85%, or actually in most cases we could. So if you see average, it is mostly 80% accuracy that we have in predicting the key. So someone might ask that now what you have is 100% key, but what you are able to predict is what you are able to predict is 80%. So that means you're predicting only 80 bits out of your 100 bit key if your key is 100 bit. But then if you look at it more carefully, right, so you can unlock most of your design with this 80% key. That means now understanding the design is possible if 80% of the key is available. And then you can easily apply Oracle guided attack on your design, right? So that or you can try to devise a mechanism where you're able to predict the rest of your key bits. Right, and this was it's also shown in the literature that it is possible. So there was a paper from Florida, Swarup Bunya's group, where they first applied the machine learning attack, and then um, they used that as a seed to retrieve the rest of the key. Yeah, so as I said, there is a lot of information leakage here because of the locality vectors that we have, and then we could retrieve a fair amount of key. So maybe going from next, there is a question again. Okay, so somebody called Hazik Ali is asking. So there are two questions now. Are the VLSI and embedded industry interrelated? Well, it's up to you how you look at it. So there is a fine line, right? So I would say they are interrelated. So I wouldn't say the somebody working in VLSI can't work on embedded systems, because skills are always upgradable. Um, but yeah, so I think it's more of a philosophical question, right? So it's up to you how you consider it, right? And if you still have some doubt, I think you can probably try to unmute and ask in more detail. Or maybe you can ask uh, a specific instance where you see that they're interrelated or not interrelated. The second question is again from somebody called HP in logic. Okay, it's logic locking. Extra gates are required. So what about the extra propagation delay? Yeah, so this is a good question. So now it's not just about propagation delay. You're also incurring a lot of extra hardware, right? So you're going to pay not just you're going to pay the price not just in terms of frequency, but also in terms of area, and by that maybe also in terms of energy or power, right? But then again, what you're trying to do is you're trying to protect your design. So just imagine a mission critical application, or an architecture that is used for mission critical application, and what would you prefer there? So would you prefer something which has some hardware Trojan inside it, or would you prefer something which is, let's say, slightly lower performance but is Trojan free, right? And yeah, just, and also maybe to emphasize a bit more on this, so our tools that we have, right, which are now also commercial, by the way, uh, they do pretty good job. So now uh, the area and energy and propagation delay, or let's say frequency uh, overhead that we incur by applying logic locking is, I would say, it's fair. So it's not that high, right? So we always try to place our key gates in such a way that we incur minimum overhead, at least in terms of frequency. So there's a follow-up question: embedded hardware engineer different from a core VLS engineer? Yes, definitely. So embedded hardware engineer might be focused more on, let's say, software, or maybe something like hardware software co-design. While if you look at the VLSI engineer, the focus could be more towards RTL coding, or it could be more towards physical design. It could be fabrication, right? So the two fields are quite different in that sense. Okay, now uh, there are no more questions left. So let's go back to the slides. So now, based on our logic locking mechanisms, we decided to extend them a bit, and then we decided that okay, let's do away with CMOS, and let's try to look into some other materials. So then I was in contact with one of my colleague in the materials engineering. So they do materials for electrical engineering basically, and they work on biosensors and silicon nanowires. So then we decided to adopt some of the ideas from from their group to incorporate in the logic locking. So the obvious thing was to replace these key gates and also part of circuit functionality by biosensors basically, right? So then these are basically sensors which are enabled by DNA. So now your DNA, or let's say not your DNA definitely, but a DNA or a synthetic DNA becomes the input key, right? Which sounds quite interesting and fancy, and that's what we are now working towards. We are trying to build a prototype where we can use synthetic DNA as a key for logic locking, right? So now, so now that's again a small example of how we are planning to do this. So again, you have an original circuit, and then you have a black box here, right? And this black box is basically your bio key gate, right? So this is a biosensitive device or DNA sensitive device that is activated, or that supplies you correct output if you give correct input to it, and which is DNA in this case. Right, so this is how the ion sensitive field effect transistors look like, and we can also call them bio key gates. right? So this is the project that we got approved last year, and we started working on it basically from October last year, and now we are pretty close to building a prototype. So just for your information, so this is not something which is only on paper. So this is something that we are fabricating now. So we are trying to build an actual prototype with FPGA board, and this bio key gets available on a breakout board, and then we will try to demonstrate that this is more effective than the standard CMOS based approaches, right? And in the last figure in the bottom, what you see is the operational principle of bioanalog. So basically, whenever you have some kind of DNA binding on the surface of ISFET, what you do is you see a shift in the voltage, and then you amplify it, and then that becomes your logic input to the succeeding circuit, right? So now,
Farhad, just the
yes,
time check. We have like 12 minutes more.
yeah, sure. I think I'll be within the time. So. Okay, so yeah, so this is how bioanalog works, and bioanalog offers uh, it has a few features. So for example, bioanalog also offers some kind of camouflaging. So you can actually you can unlock your circuit after it is fabricated, which is also true in case of logic locking. But now in case of bioanalog, what happens is, since your devices are polymorphic in nature, uh, uh, there is no way that the design house or foundry, mostly foundry in this case, can find out that what your design is actually going to do after it is fabricated. So that's one of the very big advantage of bioanalog, right? So yeah, so just to summarize my presentation till now is I mostly talked about logic locking, which is used for prevention of hardware Trojan. We also showed you the big picture. I also showed you a fabricated chip, RISC-V core with logic locking. And then we also talked a bit about the deep learning for attacking logic locking. And yeah, and then I also talked briefly about binanalog. One thing is the attack that I talked about. So we also have now published a solution for that, which was recently accepted in IEEE transactions on computer aided design, so IEEE TCAD. And maybe you can, if you want the version, you can probably email me and ask me, because as of now, probably it's not yet available. So then now next I'll quickly give you a brief idea about the neuromorphic uh, work that we have started doing in last 1 or 1.5 years. So as you know, the idea of neuromorphic computing is pretty simple. So motivation is pretty simple. You want to do low energy computing basically, right? And you want to match the power efficiency of your brain, and that's the idea here. So this is the neuromorphic projects landscape at our institute. So we have a few projects which are funded from government, um, and we are looking into neuromorphic simulator. We are looking into power estimation methodologies. We are looking into multi-scale modeling. We're also looking into row hammer-like attacks on memory-stive devices. So okay, here what you see here on the left top picture is on the left side, it's an FPGA board, but on the right side, what you see is the fabricated crossbar, right? So which is probably not so easy to get, but now because of our very good collaboration with Fortune Centrum Julish, we are able to procure this crossbars, and now we are trying to so we already have the first prototype. We are able to connect this crossbars to the FPGA platform. We're also developing compiler toolchain for neuromorphic architecture, which is called NeuroFlow. And we're also doing a lot of security evaluations in the form of thermal side channels and covert channels here, right? So yeah, so this is on the previous slide, what you see so is the wafer scale or wafer for memory stick crossbars. Here what you see is the package crossbar, and these are procured from Fortune Centrum Jülich, which is like 30 kilometers from Aachen within Germany. And on the right side, what you see is the ARC1 prototyping system. So this is we procured from some university in UK. I forgot the name, but I can get you the name if you want. And it has some simple Python GUI, and the capabilities are a bit limited, so you can do perform reads and writes on the crossbar. But those are sufficient for us to identify if the crossbars are working correctly or not. And as an attempt to be a leader in this domain, we are also developing a neurolab. So what you saw in the previous slide was the neural lab version V1, which is already existing. And now in the near future, we plan to procure more devices that can do wafer scale probing, and we also plan to acquire a few test and function generator test devices and function generators to have a well-equipped neuro lab where we can perform a lot of experiments, and we can procure we can procure some projects and do some nice prototyping research. Yeah, so now to summarize my talk. So yeah, so I just briefly talked about um, our neuromorphic attempts and our neural lab initiative. And as I mentioned before, I also talked a bit about logic locking, and I also gave introduction to our institute. So yeah, we always have open positions, open PhD and postdoc positions. And if you think you're bright, please apply. Yeah, so then thank you. And if you have questions, feel free to ask.
So we've enabled participants to mute themselves, and if you have any questions, please unmute yourselves and you can ask.
Yeah, before that, thanks, Dr. Farhad. I think very, very interesting, very informative talk. And thanks for taking out time. So on behalf of IEEE CAS Bangalore chapter, really want to extend our thanks. And maybe we'll open up for any questions. We have a couple of minutes, so please come forward. And if you want to ask, go ahead. And also, I want to thank that for the offer, especially a lot of people in this, I think, the webinar from the academia, a lot of researchers, students are there. So it's really great opportunity. If anyone looking forward for the postdoc or research opportunity, please reach out to Dr. Farhad.
Hello, sir.
Yes.
Good evening, sir. This is Gajendra, Tamil Nadu, Sarpam College of Engineering. Sir, I have one small doubt. Actually, your work was wonderful and is amazing. Many things are new to us. And my question was, so unfortunately, if your system is failed or it is attacked, so do you have any secondary provision to pick up your chip to work or overcome from that issue?
Yeah, so see, there it depends on the attack, right? So if you're talking about some kind of malware, then we do work on malware. And not to your surprise, I actually work very closely with IIT Madras there. And we are developing a prototype there where we are trying to detect malwares being executed on embedded devices, right? So that is one sort of attack, right? Now then there are different types of attacks. So there could be some side channel attack, right? So for different attack, you are going to have different mechanism. So you can't say that I have one master mechanism that would solve all my attack problems. So that's not realistic, right? So if someone claims that, I would be quite surprised, and I would question it quite
Sir,
well.
what may be the cost comparison between the ordinary one and this attack feature? What may be the percentage of cost for the chip?
So the cost, as in if you're talking in terms of euros or rupees, I think yeah, it will be expensive because you always pay for security, but it will not be very expensive, right? So it's like since we have put a lot of efforts, it will be like slightly more expensive than the other state-of-the-art solutions. But again, what you're getting is a secure solution here, right? So, and if you're talking about cost in terms of area, energy, and delay, I think we already discussed this in one of the questions.
Thank you very much.
Hello.
Yes.
Yeah. So without much of a lab resources, how can we contribute to risk 5, the chip you were talking about?
Okay, so first of all, we don't contribute to RISC-V, to be fair to you. Now what we do is we are more of a user of RISC-V, because now if you look at the RISC-V community, there are already quite a few open source initiatives, right? So there is, I mean, there are quite a few. So for example, if I tell you the ones that I know, you always have this one from Rocket Group, so which is coming from UC Berkeley. Then we have one from IIT Madras, we have one from ETH Zurich, we have one from BlueSpec, and there are many other. So our objective is not to contribute to RISC-V. Our objective is rather to use RISC-V,
Okay.
right?
Okay.
So yeah, I mean, if there are some security related solutions, we would definitely be glad to contribute in RISC-V community there. But yeah, so but as you already saw, so ours is more of a commercial product. So then contributing to an open source could be somewhat tricky, right? So
Right.
but that doesn't mean that we are stopped from doing it. So if you can also with minimum lab resources, you can definitely contribute, because a lot of the simulation tools that are being used in RISC-V community are also open source, right? So for example, a lot of them use Veriletter, iVerilog, which are openly available. um, and yeah, I think there are also some test tools, so all this test and everything is only available. Only place where you might have to pay a bit is if you want to prototype it on FPGA, but I think that's also not that expensive if you go for something like 200 euro to 500 euro FPGA board from Xilinx.
Okay, sir. Okay. Thank you. Thank you so much.
A question in the chat box.
Sure. Which one?
So there is one which says, in your opinion, if a person wants to pursue his master's, would VLSI or embedded be a brighter future?
Okay, that's it's a bit difficult to answer, right? So if you're bright, your future is bright, right? So that's how it works. So
Excellent
it
answer.
doesn't matter whether you're VLSI or embedded, right? So both the domains are quite good, and you can do well. So you can do well in any field, right? So that's my opinion. So again, because you asked for my opinion. So.
And I think we'll take one last one for the day. There is someone who asked, if you want to join the RISC-V community, do we join them directly or as a company? And is there any fee or anything of that sort if you know about it?
No, could you repeat the question? Actually, I did not get it.
Sorry, again. So the question is, if a person wants to join RISC-V community, can he join in as an individual or he needs to join through a company? And if he does so, will there be a fee to join the same?
Well, I think that you need to check with RISC-V Foundation. So I think there are these different levels of membership that you can have. So I think academic might be free or it might be nominally charged as far as I know. But I'm not member there, so I'm probably not the right person to answer any of those questions, and I might end up actually giving you wrong information. So maybe I'll just stay away from answering this question.
All right. Okay.
I think Mr. Lok has answered there is no fees to join.
Okay, great.
There's no fees.
Right. So Devesh, you want to close this session?
Yeah, I
Formally.
think, thanks, Chase and Dr. Kiran. So again, thanks, Dr. Farhad. I think taking out time, very, very interesting session. And thanks to all the participants, making it interactive and asking all the questions. And feel free to reach out to Dr. Farhad, even beyond this talk, if you have any query. And also, he mentioned about some of the opportunity for the researchers. So I think please utilize that. And with that, thanks again, Dr. Farhad, and thanks, Dr. Kiran, Jayes, and team. Thank you.
So okay, so then thank you and have a nice weekend. Bye bye.
Thank you. Thanks,
Thank you,
everyone.
Doc. Thank you.
Thank
Goodbye.
Thank you. Bye-bye.
you. team of CAS, Dr. Farhad Merchant, Mr. Devesh, Mr. Ayan, Mr. Jayesh, who just helped me out because I had some power issues, and Dr. Param. Thank you so much.
All right,
Have a
thanks
wonderful
everyone.
session.
Bye bye.